Happy Wednesday, metalheads! Today, or whatever day you happen to be watching if you're a friend from the future. Today we will be talking about the data that is in the air all around us. It'll be radio, so metal meets radio. I will be joined by Ed from my team and Luigi, who will talk to us about some SDR things. Hello!
Hello.
Hello, everyone.
Excellent. So Ed is looks well licensed. Whiskey 8 Echo Mike Victor.
Yep.
And coming to us from where?
Coming to you from Ann Arbor, Michigan.
Excellent. And yourself, Luigi, if you could tell us a bit about yourself and where you are.
Yeah, I am a computer engineering student, and I am from Brazil, and I'm here on my parents' home at the moment. And I make the Pi Sdr image that some of you may know. That is a Raspberry Pi image for the Raspberry Pi for the SDRs.
Excellent. And then I suppose we can jump right in. You said SDRs, and so if everyone's not familiar, expand it out. What is SDR?
Okay, so SDR is like a normal radio, like you that you have in your car. Like you tune in the right frequency and you receive the sound. But in this case, what SDR means is software-defined radio, and it does just like the name. It receives the signal from an analog front end and then demodulate it with using software instead of hardware. The radio in your car uses hardware to demodulate like the FM radio, but the SDR uses software. And this can be very useful if you are using with a computer. So instead of having an expensive, hard-to-make hardware to use for one application, you have a software radio that you can make. You can code to work as a FM demodulator, a digital TV demodulator, a Wi-Fi sniffer. So everything you want to do, you can do with a software radio, just reusing software and forgetting about the hardware. And the computer power is either provided by your computer, like I said, your laptop or something, or there are radios that use embedded systems like FPGAs or ASICs that can do the processing for you, and you can program them with software, or in the case of FPGAs, the firmware of the FPGAs in Verilog or VHDL.
Okay, yeah, I'm pretty familiar with listening to radio in the car and watching over-the-air television, both in the analog time and then after the switch over to digital signal. What was sort of the beginning of software-defined radio? Probably expensive initially, but...
Yeah. So everything started with professional grade hardware that is mainly used by professionals for expensive research, from professionals for companies, from universities doing LTE research, cell phones research, and they are built with extremely high quality components, like a very precise clock reference or a very sensitive analog input for the signal. And they can be very highly customizable. Like you can change the clock frequency. You can make it work with an external clock frequency to synchronize multiple radios. You can also replace the front end of the analog. So you can make it work with a different frequency or different sample rate. But they are very expensive. They can range from $2,000 to $25,000. So this is extremely expensive for an amateur, and it started with professionals on universities and companies. But later in the game, in 2012, Eric Eric Fry discovered that a USB digital TV dongle that you use to receive the analog TV, DAB, or FM can be used to receive raw samples from raw analog samples. So in
You
theory,
got one, Ed?
Got one.
Ah, perfect.
Kind of old, but the little thing here is to keep the case together. But yeah, it's a TV. As Luigi will describe, it's originally sold as a TV tuner stick.
Okay.
Go ahead, Luigi.
yeah. So in 2012, Equinix discovered that this little dongle can receive raw samples, and the community started flocking in to discover more. So they discovered what models would work with this chip, that is the Rtl Sdr, the RTL, the Realtek chipset that powers this radio, and everything went very popular very fast. So the good thing about this dongle that it costs less than $30, so it's very, very inexpensive compared to the professional grade hardware, and the software stack began to grow and grow. So we today have this dongle here that is the Rtl Sdr that is sold by the rtlsdr.com, as it's a blog that posts this kind of radios. It's the de facto standard of today. It's in an aluminum case to reduce the noise, and the signal comes in the SMA connector and comes out with a USB 2.0 interface here directly to your computer. It's very simple, very easy to use.
Yeah. I suppose I'll break real quick to say a hello back to our friends, Foss Host and Hannah. If anyone else who's watching live right now has questions, you can certainly drop them in the chat, and we'll look to get them answered for you. So the Rtl Sdr, $30 USB straight into your computer. What other units are there? What other devices? If you have a little bit more, but maybe not $25,000 more.
So after 2012, everything went very popular, and some manufacturers started to make some purpose-made SDRs using the Rtl chipset. This is the case of the Airspy here. I have the Airspy R2 that uses the same chipset, same analog front end from the Rtl Sdr, but uses a NXP LPC microcontroller to send the data back into the computer. This one makes 10 megahertz instead of this one that makes 2.5 or something like that, and it's very more sensitive to the radio also.
So that enables it to listen to weaker signals, or?
Yeah, I was talking about the bandwidth of the signal, like the amount of data you can get from the air. And the frequency range, that is the megahertz from it's like 30 to 50 to 1.7 gigahertz of bandwidth. That is the frequency range of the radio itself. And we also have here the Airspy HF that is purpose-made for the HF high frequency bands to receive, like if you are in the US, you can receive radios from China or Europe without problem with one of these, with the proper antennas and long-range radio. And after that, we have other manufacturers that made different radios, SDRs, with different analog front ends. That is the case of the Line Sdr here. This is the mini version. You can see the actual board of this unit. So I will show the chips. This is the analog front end that receives the signal itself. It will digitize the signal and pass to the FPGA, the Max10 here. And the Max10 will take the IQ sample from the analog input and sent to the computer using the FTDI here using USB. So this is the tiny little radio that can output 30 megahertz of bandwidth and going to 10 to 3.7 gigahertz. It's a bit more than the Rtl Sdr.
Can you expand those two out for me? Both the FTDR and the FPGA.
Yep, I have this one. The mini one have a Max 10 here. It receives the signal, the digitized signals with a digital interface from the analog input. That is the LMS chipset here. So the analog input, the analog part is just the first one here, and then the data is all quantized in digital signals and goes to your computer like the IQ, that is the real the complex samples from the ADC that is housed in the analog housing here, the analog IC. And the FPGA runs the software to filter the signal to make it more easy to work with on the computer. And
those are what, the field programmable gate array?
Yes.
And so that can be after the chip is shipped, the configuration can be slightly altered.
Yeah. You can. In this case, the FPGA code here is open source. The hardware is open source, so you can get in the middle there and write your own modules. I think someone wrote a FFT module to digitize to transform the complex IQ to a frequency domain signal inside the radio itself, so you don't need to spend much resources on your computer to make this conversion. So it's very, very customizable there.
It's like getting even deeper into radio. What is an FFT and why is it required to? So the T is transformation Fourier.
Fast Fourier transformation.
Yes.
Fast Fourier transformation. It gets the complex-based signal that the ADC generates. That is a time-based signal. So you can picture this as a sine wave, a sine wave. Yeah. And the FFT will just takes this time-based domain and converts it to a frequency domain. So it will make instead you will have a 0 to X megahertz of frequency, and the y-axis will be the amplitude of this signal. So if you have a single sine wave at 60 hertz, you will see after the FFT a single peak on 60 hertz of a amplitude of 0 dB. So everything can be done on your computer, or in this case with a custom module you can make on the little radio here, because you need to. FFT can be very expensive for slow hardware, so you can do that in the software. And this is a big brother of the Lime Sdr here. It's a very, to put in perspective, is very.
The scale makes sense there.
Yeah. It's the same chipset, or the analog chipset, the LMS, from the Kickstarter campaign. And this is a bigger cyclone for FPGA that can be programmable. In this case, you also have a DRAM cache to make fun things with the signal. If you need to process with a FIFO or something, you have the DRAM here. And in this case, we have another interface to the computer using, in this time, a FX3 from Cypress that makes the USB 3.0 interface with your computer. And this is the big brother. I think it gets 30 megahertz from 100 kilohertz to 3.7 gigahertz of frequency range.
And what's the antenna interface there? I didn't notice any other like SMA or BMC connectors into the.
Yeah, I don't quite remember the name of this. Those maybe Ed can remember.
Oh, like the little teeny ones that are on the board.
Oh, yes.
Yeah,
U.FL, is that what it's called?
I think so. I think so. This one golden connectors here.
Yeah, it looks like it
okay.
has
Yeah, there.
half a dozen or more of them.
Yeah, there are
Those-
a lot of channels in this radio. You can transmit and receive 2 times 2 streams. So it's 4 streams at the same time with a single radio. So you can do a lot of stuff with this one. It have a matched input from HF to VHF and higher. So it has more than 9 inputs of this radio right here. The cut down version that has only the transmit side and the receive side.
Okay.
Luigi, do you have any of the radios that have multiple receive inputs, like the Kerberos Sdr?
Yeah, this one have you can receive 2 channels and transmit 2 channels, but this is the only one with the MIMO I have. I also have the Pluto Sdr from Analog Devices that uses a professional grade analog IC that digitalizes the signal and sends to a different kind of FPGA. It uses a ZinQ that has an ARM core built in with the radio, so you can run software inside the radio. The interface is a micro B. So you can, and this is OTG, so you can plug in a Ethernet adapter here and work with the Pluto Sdr from the network. So this is a good addition, because sometimes your computer is in your desk and you need to put your radio in an antenna outside. So this can be very, very useful in this case.
Very good. Seems that folks like like the show and tell so far. What else can be? Those are the pieces of hardware and the software inside them that we don't quite see but understand is there. What are the sorts of things that you're able to do with them? Are you able to show us any either examples of taking and demodulating the signals that are around you?
Sure, I will share my screen here.
Okay.
And I can open GQRX, that is a software that interfaces with the radio, that is open source also.
Yay for open source. And then another question was any written resources that you'd recommend for beginners to learn about this? I learned better by reading and would love to know more. So I noticed that in show notes there's a few links, and so we'll both drop those in the chat, and then also over the course of the show drop a few links into chat, and then in the future video. But yeah, there absolutely will be places to catch up on more, and then certainly Luigi's both website and GitHub and Twitter are full of good stuff.
Yep.
You said screen share. There we are.
There we go.
So this is the GQRX program. And you can see here in the top level here, you can click in this bar here. And you can choose the configuration of your SDR. In this case, I'm using a Lime SDR. That is this one tiny here. And I am running it on 30 megahertz, that is from the bandwidth. And oops, I did something that I shouldn't. So this is from 512 megahertz, that is a UHF signal. And this blocks here is the digital television from Brazil. It's called ISDBT. That is a Japanese standard that we use a modified version here. It transmits raw MPEG format. So you can take this recording, you can just record this, take to the software, and it will demodulate for you, and you get a transport stream that is a MP4 video from this one. So each channel here has 6 megahertz of bandwidth, and you can send up to 4 streams at the same time, 4 screens, like for 1080p streams at the same time, using the single carrier that is this box here, separated with a 500 megahertz spacing between all the channels. And we also have in 1.8 gigahertz the LTE signal. These fasting blinking thingies here are the uplink. So these are the phones talking to the cell tower, and this contiguous block at the side of this blinking signals is the downstream of the LTE. So this is the actual data that comes to your phone. It's a contiguous stream for everyone. Every device demodulates this, and only takes the part that is meant for you. So you don't need to make some clever frequency multiplexing things with the downlink, and you save space in doing that. Close to the LTE signal in 2.4 gigahertz. I am sure you heard of this frequency before. We will have your Wi-Fi frequency. It's kind of very busy right here, so we can see all these packages coming from the air. I will hold here to see the pattern. And these are single packages, IP packages coming from your router to our phone. And you can see some interference here with some networks talking on top of others, and other tiny signals. If I can, oh, there we go. These tiny signals here that it can be Bluetooth or other types of transmitters, like mouse transmitter, keyboard transmitters, uses a narrowband signal. So the 2.4 frequency is a open frequency that almost any devices with proper certification can transmit. So this is very, very busy here, using all kinds of protocols, all kinds of signals hanging around this frequency here. And we also have the FM band that is quite lower at 100 megahertz or so. And these tiny things here are your FM radio and the analog version. In the US, you have like the digital TV, a block thingy here on each side of the band to send the digital FM radio to our radio.
And so each one of those spikes and then the lines that they're drawing in that time chart is a individual FM radio station. So like 90 point, what is that? Probably like 91.1 or
yeah,
or 90.2 or 90.3, I guess. I think they're on in the US anyway. I think they're on all the odd numbers.
Yeah, it varies a lot from country to country, the frequency plan there, but it's almost like 240 kilohertz of bandwidth of actual signal, and some spacing between each channel. Yeah, and in the right here you can demodulate the signal. I won't demodulate because of copyright, but you can choose the bandwidth of the signal, the filter shape, or the actual demodulation. You can choose for AM radio, narrow FM, use it for walkie-talkies or ham radio, or wideband FM. That is the actual analog FM broadcast stations. And also some HF stuff, that is LSD and other types of modulations that you can demodulate right in the GQRX.
Very cool. And which computer is this this running on then?
Yeah,
Is this your laptop or?
Yes, this is my desktop running right here because you need to have a quite good CPU to emulate over 10 megahertz or so, depending on the software. But you can run this on a laptop or a Raspberry Pi with a less bandwidth, but you can run on a Raspberry Pi, for example.
So on a less powerful machine, or with a less powerful SDR, you'd see the same signals, but you wouldn't see as many of them, right? You'd have a narrower bandwidth if you were looking at.
Yeah, if you are using a Rtl Sdr, for example, you would see something like this. That is 2 radios and that's it. So you need to get in the frequency range here and toggle between the radios you need to emulate here. This is 2.4 megahertz. It's the same thing, but less radios at the same time, less frequencies.
Very good.
And from what I remember of looking at FM signals closely, it's pretty easy to tell by the spectrum whether it's music playing or someone talking or as it looks like right now, some silence.
Yeah. I think this is a commentary FM radio, and this is a music one. So we have the perfect example here.
Yeah, you can sort of tell by the way that it's the compression that's used when, I guess, mastering is you have the staying pretty much constant volume instead of quiet loud the way that words go.
Yeah. The FM radios uses some clever tricks like the emphasis of the audio to transmit better within the medium, to distort less the audio you end up getting. And these 3 points here when silence is the carriers of this FM radio. So instead of transmitting one carrier, all your power, you split the power between them. You get less interference this way. So yeah, clever tricks to improve your audio.
Yeah, so maybe small hardware now. You had talked a bit about the possibility of running on Raspberry Pis. I know that that's hardware that can cost as little as probably the entry price for those that Rtl Sdr unit may be hard to translate with international currency, but I think probably between $25 and $50 depending on what shipping and accessories and the rest of it runs.
Yeah, the Pi Sdr, the Raspberry Pi have a lot of models here. The 4 version has multiple versions of DRAM sizes, so you can get from $35, I think, to $85, depending on the RAM configuration you pick. The maximum RAM is 8 gigabytes. But you can get away with 1 gigabyte if you don't use the hardware for much things. I will share my screen with the VNC from the Pi Sdr here.
Yeah.
So this is the Pi Sdr. That is an image to your SDR using the Raspberry Pi, because this images, the open source software or the SDK for the radios can be very tricky to install. So sometimes it's easier to get a whole OS with the preloaded software you need, because most of people that are in this hobby don't know very well Linux, so they don't know to write on the command line to install a program, to compile a program that most of them need to be compiled. There is no install binaries. and they have a dependency hell that you need to install everything in the right order, or everything won't work. So there's that.
Everything in the right order and every correct version.
Yeah. If you screw up one version of the first dependency, you are screwed. Yes.
Yeah, you should be able to, I guess, capture radio without being an ops wizard or Linux administrator.
Yeah. My friend Luciano, the Sdr started when he asked me to help him to recover his Lime Sdr. He couldn't install in his Windows machine, so I take my little Raspberry Pi in the time and installed the right software and sent to him the image from the SD card image, and he flashed it in the SD card, and everything works in the first time. So I decided to publish this work to the community, and I've been releasing a version since 2019 with the pre-built system here that just works. You can install your flash card like the Raspberry Pi OS and boot the Raspberry Pi, and everything works. For example, here we can get the GNU Radio. That is an application to emulate the signal. For example, if you want to take the input from a radio, you can use the Rtl Sdr source here. That is a block. The data comes from the hardware, and these blocks will output the raw data to the flow graph. And if you need to, for example, demodulate the FM radio, you can use a wideband FM receive, and just you drag this to here and just link the both of them. And you need to make, I won't explain everything here because it can get quite complicated with sample rates. You need to decimate the signal to match the modulation rate. But the idea is that there are blocks, and the blocks are interlinked with the outputs and the sinks and inputs. After you have a demodulated signal, you can output for your audio interface using our audio sync right here. And you can notice that the color of the interlink changed. So the radio will output a complex signal, and this one will make it a float signal. This is a levels of the voltage of the signal. You don't need at this time the IQ signal, the complex signal. And so this is the GNU radio that you can use inside the Pi Sdr here. And you also can use the same software I used before, that is the GQRX, but in a smaller frequency. It will boot the Lime Sdr, and there we go. I can play, and we see the same radios here. The FFT is not the same resolution, and it's not so smooth, but it works, and you can use just to talk to monitor the frequency using just a $35 computer. So that's an accomplishment.
Yeah, that looks like a great way to get started, or even drop something remotely. Where I guess the thing about radio is it's entirely dependent on that signal, and so if your antenna or isn't where the signal is, or if you're having remote access to a machine that might be able to hear it, you can take that and then process it elsewhere.
Yeah, in fact, the Pi Sdr comes with a SOAP Sdr remote that enables you to access the SDR like they it was inside your computer, through the network. So you plug in the SDR in the Raspberry Pi, and the Raspberry Pi will transmit the IQ samples from the Raspberry Pi to your computer, and you can process the data with your computer. If you have a fast enough network, that IQ samples can be very large. So you need a gigabit network to make use of it, but it's possible.
And so that was sort of the problem solution, and then you got that to people first by, I guess, sending it out over Twitter.
Yeah. I posted the image, a link for an image on Twitter, and they started to liking it. They installed it, and then multiple people said it worked. And the first time they got their SDR working was with the Pi SDR image. So at the time, the image was hosted on a Raspberry Pi inside my network. So very improvised there. And later, I started to build up with this image. I started adding software and other features. The size of the image became a problem because the file system started to make the actual image a little bit bigger than it should. So I started using the PyGen, that is the open source build system used by the Raspberry Pi Foundation to build the Raspberry Pi. So today we run on GitHub Actions, and the whole compiling process is automated, and the release is just 2 gigabytes. So you download 2 gigabytes, flash the 2 gigabytes on your SD card, and everything works. And the server, a quad-core server takes almost 24 hours to compile everything. So if you do it yourself, it would take a long time to make the same thing you can download in 2 minutes or so.
Yeah, we had was it last week or the week before? I had talked with friends at Ampere about doing builds for ARM on machines with many cores. Ed, how long do you think a build would take on some of the, and maybe
some of
Ultra
the
or yeah?
Yeah, so I think we've got. I don't remember the exact times. The newest Ampere machines are 160 core ARM, 64-bit ARM servers. So the acid test is compiling the kernel, and it just takes. I don't remember the exact timing. The trick with multi-core systems is there's always some task that runs on one core instead of all of them. It's some linking step usually. So it sometimes takes longer than you'd hope it would. A couple minutes to do a kernel build, which is quite acceptable.
But might be able to beat the 24 hours that was.
You might be able to beat the 24 hours, yeah.
Yeah, most of the overhead is a QEMU, QEMU overhead that emulates the ARM V8 on the x86. So that's low.
Yeah. Yeah, we should try a native build and see what sort of times we can get. That would be an interesting.
Yeah, that would be wonderful, because I am rewriting the code to install the image in Ansible. So this can be quite useful. I can modify the code to run natively and compiles everything using not using QEMU.
Not using QEMU. Yeah, we had one project that saw. This was Balena, I think, that moved from QEMU to native builds, and expect a 5 or 6 times improvement, just because of the overhead of emulation.
Yeah, that's great. That's great.
Yeah, I look forward to seeing the results of that if we can get that. If we can get that set up.
Yeah, let's talk about it.
Yeah. So Luigi, have you have you done any work with Kiwi SDR, the international network of remote SDRs that you can tune into from anywhere?
Yeah, not yet. I don't have a unit, so I can't make some contributions with the project at this time. But I'm planning to get one in some time.
Yeah, it's interesting because it's you don't have to own an SDR to listen to one, and there's a network of them all over the world. Mostly, I think the typical one is like a 4-user maximum login, so not a mass market phenomenon by any means. But you log into a radio in Tokyo and listen to what radio sounds like in Japan, or you log into a radio in Brazil and listen to what radio sounds like in Brazil. That the typical Kiwi covers from 0 to 30 megahertz, plus or minus something. So long wave, short wave, most of the lower hand bands, but not TV and not FM radio.
Yeah, this kind of distributed networks is kind of starting to pick up right now with the upload speeds getting better and the hardware getting faster, like that Pi SDR, the Raspberry Pi SDR, the Raspberry Pi, with a higher processing speed, because each client takes a lot of processing, so that's a kind of a limited factor right now. But it's a wonderful thing because you can, like you said, to access radios all over the world using this network of interconnected radios.
And so there's not just radios on Earth, though, right? So we talked, I think, mostly about terrestrial signals, but there's also radio coming at us from space. We've put countless satellites up there, and outside of seeing them through a telescope, I think the way that they're communicating is also radio.
Yeah, the rockets kind of tend to use the S-band signal that is from 2.4 gigahertz, and most of the high-speed modern satellites of the lower orbit use X-band, that is 10 gigahertz, or the legacy ones you can receive on your home using the Rtl Sdr with the 137 megahertz. So it's quite low, but the resolution is low, and it's noisy, the quality of the image. But there are some bleeding edge satellites like the NOAA 20 that transmits in the X-band a 250 meters per pixel resolution, so it's big. The file sizes are also big. You need a automated dish of 3 meters or higher or larger to receive the signal. You'll need a specialized SDR to quantify the signal and transmit to your computer. And you can't do it in the real time because there is too much data to process. So you need to record this in a fast drive and later decode offline. So I wrote the original open source demodulator that is used to demodulate the NOAA 20. It took a lot of work to do because they almost all satellites use a protocol called CCSDS, that is a commission for space that tries to pattern to make a common all the data links. So the NOAA 20 used this data link, the CCSDS, and we and my friend Lucas Teskey started this project called Open Satellite Project that aims to decode lower orbit satellites, and like the GOES, that is and the GOES, that is a geostationary satellite. The geostationary satellite, I have some recordings here that Jeremy can show.
Like this one?
Yeah, this one. So the satellite is stopped in relation to the surface of the Earth. So the image looks static. So this is the same orbit used for the satellite TV to make that you don't need to move your dish every time. And this is a weather satellite, so it takes pictures each 15 minutes and sends down to Earth. It's very useful to make some disaster prevention. It's used by meteorologists from all over the world. You can see a single satellite here can cover a third of the planet. So it's a very cost-effective way to monitor the global climate. And if you look closely, you can see some hurricanes originating on the east coast of Africa and coming to the Florida. I think this is 2019. And so if you switch to the colorful video, you can see it better because it uses infrared. This is another light frequency imager that sends the same amount of images, but this time we can see the temperature of the atmosphere. And this is an overlay with the temperatures in kelvins. So the purple ones are the coldest, and the white is the hotter. So you can see some hurricanes coming out of the right, going to the left in the United States, in a very particular season of the year. So this is on the peak of the hurricane season of 2019, and the hurricanes just go blasting from the Africa to the United States. In some cases, you can see dust from the desert of Sahara coming to the Amazon here. You can see with the higher resolution imagery quite visibly coming from the other side of the Atlantic. So this is quite a great resource that NASA have to monitor the climate.
Wow. That's beautiful.
Yeah. If the NOAA wants to focus on a hurricane coming to the coastal United States, they can draw a little rectangle inside the hurricane and get an image each 1 minute or so. So this is extremely fast temporal resolution that we can do these days.
Very good. Oh, yeah, that was good. Sorry.
Luigi, what kind of antennas do you need to pick up the satellites? You said that the some of these are within the range of what you can do with an RTL.
Yeah, you can use the $15 antenna from the rtlsdr.com website. That is quite versatile. You can receive radio, TV, digital TV, and also the NOAA and Meteor satellites. I don't have the URL right now, but I can post somewhere afterwards. The antenna is like a TV antenna, so but there are some clever things you can do to make the antenna reject some bands and accept some other bands. Like it's called VD pole. So you need to fold your antenna. That's the ground and the core. You fold the antenna in 45 and 60 degrees, and the antenna will start picking up the 137 megahertz frequency band that these satellites are transmitting. You can to know if a satellite is passing ahead of your location, you can use another software that is free open source called gPredict, that is made by the same person that writes the GQRX. And you can get a schedule when the satellite will go overhead and the elevation of the satellite. And you can program yourself to go outside, set up the antenna in the right direction, starting recording the signal, and then demodulate it. This is a quite good exercise for beginners. It's very, very fun to do. So the Rtl Sdr.com has a lot of tutorials how to do this. If you search for the VG pole antenna, you can do it yourself using copper wire or something. Or if you want to do if you don't want to do this, you can just buy the antenna that they sell in their store. And we have also this one right here that is the Jetson Nano. It's from NVIDIA, that is meant for machine learning, that also can be used for SDR. The next version of PySDR will support this one. And the important thing about this one here is the built-in Maxwell GPU that you can run CUDA inside. So this tiny little board can run CUDA applications and do some really cool GSP that a computer would struggle doing on the CPU.
Excellent. Yeah, we will already linked, I think, that PySDR image, but yeah, I think if you're watching, you can find Luigi at Luigi F Cruz on Twitter, on GitHub also, and there's the projects and repos listed out there. As we come closer to the close of the hour, was there anything that you wanted to leave folks with, or have we done a solid job of cover?
Yeah, we're quite. We talk about
a good speed run. Yourself, Ed?
Everything looks great. I'm having used the Rtl Sdr for a long time myself. I'm impressed by some of the capabilities of the slightly more expensive ones, just wider bandwidth and better setups. But if someone wants to get into this hobby and just try things out for themselves, my own sense for it is that the Rtl Sdr is a very inexpensive entry point that's fairly forgiving in terms of setup and whatnot. I mean, even if you just want to listen to broadcast radio and just say that you did it, and then start looking around for other signals that are of interest.
Oh yeah, and I suppose also to mention, if we're talking radio, behave yourselves, viewers. Get licensed if you're going to transmit.
Very much so.
All right. Well, that looks like it'll be good for now. Then we will thank you Luigi for joining us. Thank you Ed for joining me here, and we'll see y'all before long, metalheads. You can follow along for the next one at twitch.tv/Equinix Metal, and we're also Equinix Metal on the Twitters. Bye now.
Thanks, everybody.
Thank you for inviting me.